Welcome to week 3. This week explores named entity recognition, or NER for short, which is a subtask of information extraction that locates and classifies named entities in text. The named entities could be organizations, persons, locations, times. For example, if you look at the sentence, "The French people are visiting Morocco for Christmas," you will see that the word French is a geopolitical entity, Morocco is a geographic entity, and Christmas is a time indicator. When you can recognize named entities in text, then, given an article, you can find the people, countries, organizations that are mentioned, and you can quickly parse and gather information about it. You can use this information, for example, to do market research about certain topics by scraping the internet. When implementing NER for this week, you will be using a long short-term memory unit, or LSTM. LSTMs are similar to RNNs and GRUs, except they have other gates that make them more powerful. Jonas will show you more about it.
Yay, let's get started. Welcome! This week I will talk about long short-term memory cells, which we call LSTMs. To understand why they're important, let me explain the vanishing and exploding gradients problems faced by conventional RNNs. So let's dive in.
First, I'll talk about backpropagation through time. Then, I'll introduce you to vanishing and exploding gradients, a problem common to RNNs, and I'll show you a few ways to handle them. Let's begin with a discussion of some of the pros and cons of using a recurrent neural network. For one, the way plain or vanilla RNNs model sequences work is by recalling information from the immediate past, allowing you to capture dependencies to a certain degree. They're also relatively lightweight compared to the other n-gram models, taking up less space and RAM. But there are downsides. The RNN's architecture can struggle to capture long-term dependencies, and RNNs are prone to vanishing and exploding gradients, both of which can cause your model training to fail. Vanishing and exploding gradients are a problem that can arise due to the fact that RNNs propagates information from the beginning of the sequence to the end, starting with the first word of the sequence, the hidden value at the far left. The first values are computed here. Then it propagates some of the computed information, takes the second word in the sequence, and gets new values. You can see that process illustrated here. The orange area denotes the first computed values, and the green denotes the second word. The second values are computed using the older values in orange, and the new word in green. After that, it takes the third word and the propagated values from the first and second words and computes another set of values from both of those. And it continues in a similar way from there. At the final step, the computations contain information from all the words in the sequence, and the RNN is able to predict the next word, which in this example is goal. Note that in an RNN, the information from the first step doesn't have much influence on the output. This is why you can see the orange portion from the first step decreasing with each new step. Correspondingly, the computations made at the first step don't have much influence on the cost function either. The gradients are calculated using backpropagation through time, which sounds way more scary than what it really is. As with simple backpropagation, you just have to apply the chain rule multiple times. Recall that the weights W subscript H and W subscript X are the same for each step. And let's focus on the weights W subscript H, noting that everything that I'll present to you also applies to W subscript X. With the loss being computed at the T step of the sequence, the gradient with respect to W subscript H would depend on the computations that are made at every step. In fact, it is proportional to the sum of products of hidden states partial derivatives. This relationship can be found by applying the chain rule and the use of a couple of tricks. But you don't need to worry about the derivation as much as the implications behind this formula. Let's take a closer look at it. The term inside the sum, the product of partial derivatives, is the contribution of hidden states k to the gradient, and the length of the product sequence for each k is proportional to how far the step k is from the place where the loss is computed, in this step, t. So as you look at hidden states that are further away from the place where your loss is computed, the partial derivative products start to become longer and longer. For instance, the contribution to the gradient of a hidden state that is 10 steps away from step t, you would have to compute a product of 10 terms. Therefore, if the partial derivatives are lower than 1, the contribution of the hidden state to the gradient approaches 0 as you move further away from the place where the loss is computed. Conversely, if the partial derivatives are greater than 1, the contribution to the gradient goes to infinity. The first case is known as the vanishing gradient, and it causes the RNN to ignore the values computed at early steps of a sequence, while the second case is known as exploding gradients, which causes convergence problems during training. Now that you're terrified of vanishing and exploding gradients, let's discuss some solutions. I won't spend a whole lot of time on this, since this week focuses on a model approach that was designed to mitigate this problem. You can deal with vanishing gradients by initializing your weights to the identity matrix, which carries values of 1 along the main diagonal and 0 everywhere else, and using a ReLU activation. What this essentially does is copy the previous hidden states, add information from the current inputs, and replace any negative values with 0. This has the effect of encouraging your network to stay close to the values in the identity matrix, which act like ones during matrix multiplication. This method is referred to, unsurprisingly, as an identity RNN. The identity RNN approach only works for vanishing gradients though, as the derivative of ReLU is equal to 1 for all values greater than 0. To account for values growing exponentially, you can perform gradient clipping. To clip your gradient, simply choose a relevant value that you'll clip the gradients to, say 25. Using this technique, any value greater than 25 will be clipped to 25. This serves to limit the magnitude of the gradient. Finally, skip connections provide a direct connection to the earlier layers. This effectively skips over the activation functions and adds the value from your initial inputs, x, to your output, or f of x plus x. This way, activations from early layers have more influence over the costs.
Now you understand how RNNs can have a problem with vanishing gradients. Next, I'll show you a solution, the LSTM. Let's go to the next video. LSTMs, as I've mentioned before, are the best known solution to the vanishing gradients problem. Let me tell you about it.
Now, I'll give you a high-level view into the LSTM model, what its architecture looks like, along with a few examples of what they're used for in the real world. The LSTM is a special variety of RNN that was designed to handle entire sequences of data by learning when to remember and when to forget, which is similar to what is done in the GRU. An LSTM is essentially composed of a cell state, which you can think of as its memory, and a hidden state, where computations are performed during training to decide on what changes to make. And an LSTM has multiple gates that transform the states in the network. The cell state travels through these gates that track inputs as it arrives. Each one plays a part in deciding how much information to pass along and how much to leave behind. The series of gates allows the gradients to flow, avoiding the risk of vanishing or exploding gradients. Let's take a moment to relate this concept to something you might find a bit more familiar. Imagine receiving a phone call from your best friend. At the time your phone rings, you might be thinking of any number of things unrelated to your friend. When you answer the call, you put aside those unrelated thoughts while retaining anything that concerns the both of you. As your friend gives you some more information on why he is calling, you'll be thinking of what else might be relevant to talk about. With the input from your friend and whatever relevant information you had in mind, you'll start the conversation with him. You'll then continue to evolve the conversation in this way until you hang up. At the end of the call, you'll have a memory with the most relevant information from your conversation. That's how an LSTM works. It updates the cell and hidden states constantly, using multiple gates, so that relevant information is passed along the network and used to produce outputs. Let's take a look at the basic anatomy of a typical LSTM unit and what each part does. An LSTM stores information in the cell and hidden states, which are denoted by C and H, and as with the vanilla RNNs, you have inputs X and outputs Y. On a LSTM, there are multiple computations performed within a single unit. Here, the information flows through three different gates. First, you have the cell states goes through a forget gate. In this step, the input and the previous hidden states are used to decide which information from the cell state is no longer important and throws it away. Then, the input gate is used to decide which information from the input and previous hidden state is relevant, so it is added to the cell state. And finally, the output gate determines the information from the cell state that is stored in the hidden state and used to construct an output at the given time step. Before diving deeper into the math, let's discuss some of the many applications of LSTMs. As you might have guessed, it is very handy for building language models, spanning use cases from predicting the next character of your email to building chatbots capable of remembering longer conversations. Music composition can be done with LSTMs, and this approach makes a lot of sense, considering that music is built using long sequences of notes, much like text uses long sequences of words. Other cool applications are automatic image captioning and speech recognition. In overcoming the problems of a traditional RNN, the LSTM has become an incredibly popular tool with a wide range of uses, and has helped evolve NLP in some exciting ways that I'll discuss in more detail towards the end of this week. In summary, LSTMs are a solution to the vanishing gradients problem, and that typical LSTMs have cell and hidden states, and three gates, which are the forget gate, input gate, and output gate.
Now you understand the LSTMs on the high level. But what exactly is the math behind the LSTM computation? I'll show you this in the next video. In this video, I will show you in more detail the architecture of a LSTM and the computations that are made inside a single cell.
As you might recall from earlier, in a typical LSTM, you have a cell state, a hidden state, inputs X and outputs Y. You can think of the cell state as the memory of your network and gets modified using information from the inputs and the previous hidden states. The gates in an LSTM decide what information is kept or added and selects the outputs at every step. You will typically have three gates. The forget gate, used to decide which information is kept and which is discarded from the previous cell state. The input gate, that selects the relevant information from the input and previous hidden states. And the output gate, that determines which information from the cell state is used as output and stored in the hidden state. Sigmoid activation functions with different trainable parameters are applied to the input and previous states for the three gates. The use of the sigmoid ensures that the values for the gates are between 0 and 1. In practice, the values encountered in the vectors corresponding to each gate are very close to either 0 or 1. With a value of 0, the gate is closed, so information doesn't get through, while a value of 1 would let information flow freely. Another significant computation made inside an LSTM is the candidate cell state. To get it, you have to transform the information from the previous hidden state and the current inputs. A hyperbolic tangent activation function is typically used in different implementations. It shrinks the information from the previous hidden states and the current inputs to be between -1 and 1. This nonlinear transformation has been used in the past because it improves training performance. However, you could try other activations and test their behavior. With the forgotten input gates and the candidate cell state, you can update the cell state. To get the new cell state, you add the information from the candidate cell state that passes through the input gate to the cell state information that passes through the forget gate. Finally, you can compute the new hidden state used to produce outputs at a given step. To get the new hidden state, you pass transformed information from the new cell state through the output gates. Note that here the new cell state first passes through a hyperbolic tangent activation. Nevertheless, some LSTM architectures ignore this information and pass the new cell state directly through the output gates. Let's recap everything I just covered. An LSTM has three gates to decide what information is passed along the network. The forget gate decides what to keep. The input gate decides what to add from the previous hidden step and current inputs. And the output gate determines the next hidden state and the output at the given step.
You now understand the intuition behind LSTMs. In the coding exercise for this week, you'll implement LSTMs on your own. In the next video, I will show you how to use LSTMs to solve a real NLP task. Let's go to the next video. In this video, I will tell you about named entity recognition, NER for short. It's an important problem and many NLP systems make use of NER components. Let me tell you what it is.
Named entity recognition is a fast and efficient way to scan text for certain kinds of information. NER systems locate and extract named entities from text. Named entities can be anything from a place, to an organization, to a person's name. They can even be times and dates. Let's discuss labels used by NER systems in a little more detail, as they relate to your programming assignments this week. Some possible classes you might run across include geographical entities like Thailand, organizations like Google, or geopolitical entities like Indian. A few more classes you might encounter include time indicators like the month of December, artifacts like this ancient Egyptian statue, or a person such as Barack Obama. As you can see, named entities can capture and identify all kinds of things. Say you have the following sentence. Sharon flew to Miami last Friday. A named entity recognition system would extract and classify Sharon as a personal name, Miami as a geographical entity, and Friday as a time indicator. You'll notice that here, B- denotes an entity of some kind, and all the other words are classified O for filler word. You can probably already see how useful this is for content classification. In a scenario where you need to search large amounts of text for certain words, say Manhattan and Brooklyn, or Toyota and Subaru, this becomes handy very quickly. Here are some real-world applications of named entity recognition systems. I mentioned their ability to scan documents for certain things quickly, so just imagine how NERs can optimize search engine efficiency. In this case, the NER model scans millions of websites once and stores the entities it's identified in the process. Then the tags from your search query are simply matched against the website tags. The same concept extends to making recommendations, where the tags might instead be extracted from your history and compared to similar user histories, in order to recommend things you might want to check out. This also applies to matching customers to an appropriate customer service agent. This works similarly to a phone tree, where you would be prompted to provide some information about your request. If you are using an app to communicate with your car insurance company, you might provide some spoken or typed information, such as, I need to add another vehicle, or my car was destroyed by a giant flying squirrel. You then be matched to the appropriate agent accordingly. Another interesting use case is automatic trading. For example, you could imagine building a web scraper to get news articles of the names of certain CEOs, stocks, or cryptocurrencies. Then, feeding those articles into a sentiment classification system and making your trades accordingly. NER systems have many applications in the field of deep learning. I just gave you one potential moneymaker for free.
Now you know what named entity recognition is. I think it's really interesting to see the many places where it is used. In the next video, you will implement your own NER system. To train a NER system, you have to follow several steps, for converting text to numbers all the way to making the prediction. In this video, we will explore all these steps. Let's dive in.
I'll show you how to convert entity classes and label data into arrays of numbers that correspond to one another, and how to create a data generator to process your data in batches, saving you time and resources. So let's begin. First, you will assign each entity class a unique number. So for example, a personal name might be 1, geographical location might be 2, and the time indicator might be 3. Next, assign each word a number that corresponds to its assigned entity class. So, given a sentence like, Sharon flew to Miami last Friday, you'll get a corresponding tokenized sentence, where 4282 corresponds to the index of Sharon. 853 corresponds to flu. 187 corresponds with 2, and so forth. The O corresponds to the O class, which denotes a filler or unrecognized word. Note also that the numbers you see here are random and are assigned when you process your data. From this point, each sequence is then transformed into an array of numbers, where each number corresponds to the index of the labeled word. So from a labeled sentence that looks like this, you'll be transforming it into a numerical array. When processing the dataset, you need to represent each word in the vocabulary as a number, as you just saw. This gives you numerical arrays, but if the arrays are different sizes, you'll need to handle that, and here's why. LSTM networks require that all your sequences are the same length. To assist with this, you can set the length of your sequences to a certain number, and add a generic pad token to fill all the empty spaces. You'll be implementing this in the assignment. But don't worry about it. It's a relatively simple process, and I'll show you exactly how to do it. In order to train this named entity recognition system, you'll first create a tensor for each input and its corresponding label, as you saw before. Then, create a data generator to output them in batches. The batch size can be anything you want, but normally, you'd want a batch size that is in a power of 2. So something like 64, 128, 256, 512, and so forth. Doing this will speed up your processing time considerably. If you felt alarmed by the words, create a data generator, don't worry about it. There will be more on this to come. After the batches are generated, feed them into an LSTM unit. You will run the outputs from this through a dense or fully connected layer. Then predict using a log softmax over k possible classes, where k corresponds to the number of possible outputs. Using log softmax instead of softmax is important here, because log softmax gives better numerical performance and gradient optimization. Let's take a look at a visual of this process. Here are the inputs, which include the arrays you created when processing the data. You'll feed them through an LSTM layer, with its series of activations and element-wise operations, run the outputs of that through a final dense layer, which is a linear operation on the input vectors, and then you compute a log softmax to get the corresponding output. Here's what the layers might look like when you're implementing them in this week's assignment. For your dense layer, you'll want to pass in the dimensions of the tags arrays you just created. Now you're ready to accomplish some mighty tasks, like numerical array conversion with token padding, training in batches for faster processing, and running your model through its final dense layer and activation function. You've come a long way since the beginning of this course, just a bit more to go.
You finally know how to train a NER system from scratch. In the next video, I will show you how to evaluate your system. Now that you have trained your NER system, you need to find a way to evaluate it. In this video, I'll show you how to do that.
To evaluate your model, you'll want to start by passing the test sets through it to get your predictions. Then compute the argmax, or the point where your function reaches its maximum, across the prediction array. You'll also need to make sure your arrays are padded using the pad token, which makes your arrays the same length. At last, compare the outputs against your test labels to see how accurate your model is. This is how those operations might look in Python and NumPy. Note that the argmax function takes an axis parameter. To indicate this accurately, you'll need to consider the dimensions of your array. Here, it's set to 2. The mask variable is where you'll identify any token IDs you need to skip over during evaluation. One token you might want to skip is your pad token. Think about how you might write this quickly and simply. Finally, the accuracy metric is computed by taking the sum of all your test labels and dividing it by the sum of all your mask tokens. Nice, that's right, no? You've now reached the conclusion of this week. Congratulations! And remember, when you pad your tokens, you should mask them before computing accuracy. Now you're able to process your data, generate it in batches, and test it for accuracy. You should have everything you need for the coding assignment. Best of luck with the assignment, and remember to have fun.
To recap, you have to predict on the test set, guess the argmax, mask the padded tokens, and then compare with the true labels. Now you are ready to implement this in the assignment.
You have learned a lot by now. You have an intuition behind LSTMs, and you have seen why they are more powerful than RNNs. You will now implement them in this week's programming assignment. In the assignment, you will build a generator and use it to feed the batches into your LSTM layer. You will run the output through a linear layer, and then use a softmax to get the predicted class for each word. Next week, you'll explore Siamese networks to identify the question duplicate. Good luck with the programming assignment.